So in this video, we're going to talk about the difference. We're going to talk about strength. So specifically the strength of materials. And we're going to talk about different classes of materials, specifically ductile materials and brittle materials, and how they differ and how they fail. So the first thing I want to clarify here is the difference between stress and strength. Stress is based off of the stress within a structure is based off of the loading, so like a type of loading it is, and the geometry of the structure. Right? Typically, we've been denoting that either with as shear stress, which we've been denoting with the letter tau, or sigma, if we've been denoting for normal stresses. Strength, on the other hand, is something that is material dependent and loading type dependent. Okay, so for examples include like ultimate strength, yield strength, and endurance strength. Right? So typically, it's up to the person who is designing the engineering component to choose what specific what strength to use in their criteria. So if they're using a brittle material versus a ductile material, they might use the ultimate strength for a brittle material versus a ductile material. They might use the yield strength. All right. And then if the part is going to be a static part, meaning it's not going to experience different loading cycles, they might use the yield strength be undergoing cyclic loading, they might use the endurance strength. So to account for these statistical differences in material properties due to processing size, temperature, etc., typically a safety factor is used in addition to the yield strength to best design your component. Okay? So if we're talking about so to determine the strength of materials, typically you would do a dog bone test. So something like you would do a dog bone test in tension, or you could do a dog bone test in compression. So very broadly, you can characterize these materials as either being ductile or brittle. Okay, so in the case of a ductile material, what you end up having is after a certain point, the dog bone specimen will break, and it will typically break at a 45-degree angle, right, relative to the applied force. Okay, so this is our tension or compressive force here. All right, so some examples of ductile materials would include aluminum or carbon steel. So if we have an aluminum case here, if we drew our stress strain curve, you might get something like this. Alright, so this would be for aluminum. Alright, and then if we had a carbon steel, typically steels will undergo something that looks like this, where they'll have a point where they'll have some inflection, and then they'll get to another, they'll finally fail at a different, at a higher, after plastic deformation begins. So this would be for carbon steel. Alright, now if you had something that was very brittle material, such as cast iron, it might undergo just almost pure elastic deformation and very little plastic deformation. So this would be for cast iron, which would be a brittle material. So for cast iron, um, how it would look or how it would fail would depend on the mode. So if it's in a tensile mode, and we draw our dog bone, all right, what we end up getting in tension is typically the brittle material is going to fail along the direction of the maximum principal stress, which in this case is along the applied force that's being applied. And then if we have in the opposite case, if we have our dog bone is in compression, So we have a compressive force acting on our dog bone specimen. Alright, what we end up getting typically is the dog bone will fail along a 45-degree angle, just like the ductile material. Okay. Alright, so that 45-degree angle is along the plane of maximum shear stress. So this is alright, and this is true as well for the ductile material as well. Alright, so so in short, here is that the very last thing I have to mention here is that the yield strength of the material typically occurs at the point of inflection. So for the case of the carbon steel, the point of inflection would be this point here. Alright, and then in the case of if you don't have a clear inflection point, typically the yield point will be considered will be at the intersection of the stress strain curve with an offset line of 0.002. So if we draw a line that starts at 0.002 strain, and we draw it parallel with our stress strain diagram initially, so this is has the same slope of the modulus of elasticity, alright, and at a certain point that will intersect our stress strain curve. At this point here, this would be our yield strength for our aluminum. Alright, so so from this information, from the simple stress strain information, we will be able to characterize both ductile and brittle materials, and we'll be able to determine the strength of each of these materials, which we're going to use in the next few videos in order to determine whether or not an engineering component under a given stress condition will fail or will not fail.